Good afternoon, everyone. Thanks for attending this session. Today, we are going to talk about how we migrate existing Spark 2 workloads to Spark 3 at scale in Pinterest. First, a little bit about ourselves. I'm Zreili, a software engineer at Pinterest Spark platform team, and I mainly focus on building Pinterest in-house Spark and PySpark platform, developing Spark toolings, optimizations, and new features.
Hi, everyone. I'm Zahin, and I am a software engineer at Pinterest. I've been here for 4 years, and I work on the Big Data Query Platform team. And I am focused on improving Spark SQL usability and performance. For our agenda today, I'll give you an overview of the Spark ecosystem at Pinterest. We will then go through the Spark 3 migration challenges that we faced. We will then discuss how we approach these challenges, and we'll end the talk with the results of our migration and our future plans. So Pinterest is entirely an AWS shop. We run our Spark platform on Yarn. Our Spark jobs are spread across 30 clusters, and these clusters contain about 15,000 nodes. To help our users select the right clusters for the job, we built a framework called cross-cluster routing that sits on top of these clusters and automatically routes the jobs to the appropriate cluster based on the SLA of the job and the type of workload it is running. S3 is used as our persistent data store, and HFS is mostly used for intermediate results of Spark and MapReduce jobs. At Pinterest, we have built a bunch of tooling around Spark to make it easier for our users to use. We have a profiling tool called Nebula that can profile Spark jobs and provide a flame chart. This is useful for users who want to optimize particular portions of their Spark job and need to understand where the bottlenecks lie. We also have a tool called Dr. Elephant, which is based off of the LinkedIn open source project. And Dr. Elephant will provide automatic recommendations for failed jobs, performance tuning, as well as cost tuning. For scheduling our workloads, we have an in-house fork of Apache Airflow, which can be used to author and schedule recurring Spark jobs. We also have Jupyter, which is a notebook environment where users can run interactive PySpark and Scala Spark queries. And lastly, we have a dedicated query notebook environment for Presto and Spark SQL jobs called Querybook. And Querybook allows our users to find data sets to query, as well as create data docs and charts. Both Querybook and Jupyter are powered by Livy, which is an open source tool that allows us to run code on Spark in an interactive way. Over the past couple of years, our Spark workload has dramatically increased. And this is largely due to the Hive to Spark SQL migration that occurred during this time period, and also improvements in Spark usability. Today, Spark represents over 66% of our daily workload, with over 45,000 daily jobs. This slide contains the distribution of the jobs we have at Pinterest. The main takeaway here is that native Spark represents 36% of our Spark workload, but uses 53% of the cluster capacity. And Spark SQL represents 63% of our Spark workload, but uses 45% of the cluster capacity. We also support PySpark, but that is a small fraction of our total Spark workload. At Pinterest, we allow users to use Spark, Spark Native, Spark SQL, and PySpark. Generally, Spark Native is used for jobs that require complex logic that cannot be accomplished through a query. And Spark SQL queries are used for ad hoc analysis of data and simple ETL workloads. And PySpark jobs are mostly used for machine learning use cases. Next, I'll hand the slides over to Ziri, who will discuss the Spark 3 migration challenges we faced.
Thanks, Zahin, for introducing the overview of Spark at Pinterest. The various Spark application type across multiple Spark 2 versions adds to the complexity of Spark 2 to Spark 3 migration at scale. In the next few slides, I'll talk about the different challenges we faced, the solutions we took during the migration, and share some lessons we learned in the process. As you can see in the slide, different Spark types struggle with their own unique challenges. For example, Spark Native mainly suffer from the Scala version gap, while for PySpark, more focus is put on the Python dependencies. In the meanwhile, there are some common issues shared by all Spark types, like how to automate the migration process effectively at scale. We'll talk about these challenges and solutions in detail. So we have different solutions for different hierarchies accordingly as shown in the graph. Let's dive into each hierarchy starting from the generic blockers to the unique challenges of different Spark types. There are some common concerns which we cannot bypass for any Spark types. To begin with, there's a strong necessity to make the migration scalable, as we have thousands of Spark jobs written by various teams, and migrating so many jobs manually can waste a great amount of engineering resource. It's also infeasible to set a hard deadline for the owners to finish the migration. Besides, it's tricky but indispensable to guarantee the reliability during the migration. We need to make sure the output data is consistent and correct under the new Spark version and avoid overwriting any production data during the migration. What's more, performance downgrade should be avoided at best effort or even be better to get detected beforehand. And if migrated Spark jobs break in new version, we need a way to quickly recover. So what should be the right direction to address these tricky challenges? If we think it further, we can see the migration steps are actually duplicated for all Spark types. For complete migration lifecycle, we need to first perform the test run under the new Spark version, then validate its output. After that, we may need to tune the performance if needed. Once everything is ready, we can go ahead to migrate job in production and roll it back to original version if anything wrong happened. Then, can we generalize and automate the entire migration lifecycle at scale? The answer is yes. In Pinterest, we built an auto migration service, or say AMS, to automate the majority of the migration lifecycle. There are two AMS separately. One is for the Spark SQL and one is for Spark Native and PySpark. The reason is the Spark SQL jobs focus more on the SQL sentences, while the Spark Native and PySpark share more common on the Spark API, but the general designs are the same. So this is the overview design of the auto migration service. The AMS is made up of two parts, the offline process, which performs migration, and the online process, which takes care of the version switching after the migration. So starting from the offline process, first we have a daily ingestion pipeline to collect all existing Spark 2 jobs, which will be onboarded later on into the AMS MySQL tables. After that, the AMS workers, or say AMS state machines, which are scheduled as the Apache Airflow tasks, will pick up these jobs from the database and start the migration lifecycle. Once the migration is done, the online process will begin to function. We created a hook that will interact with the AMS database during runtime. The hook will intercept the job's shell command and override it with the new Spark version and the tuned configurations. We also provide UIs for the AMS to easily visualize and manage the migration process. We'll dive into more details in the next slides for some key components. Let's first take a look at the target job collection process. We offer two ways to ingest a job into the AMS database. The most common way is the batch ingestion by a daily pipeline that queries and aggregates the desired job information, like the output info and resource consumption, and then dump them into a Hive table as the candidate Spark job source pool. Then we provide CLI tools to quickly ingest those jobs from the source pool into the AMS MySQL tables. The other way is to ingest the jobs on demand. On our AMS UI, there's a button which we can click and enter some basic job information, like the picture shown here. And then on the back end, the AMS will automatically fetch all needed information and onboard it into the AMS tables. Then let's get more details about the core part, state machines. So each AMS workers will go through these state machines for each job, which represents the complete migration lifecycle. The job starts in the new state at creation time, and when it's picked up by the AMS workers, it will enter the prepare config state and collect all needed information. Once the preparation is ready, the job will enter the run Spark new version state to trigger a test run under the new Spark version. And after the test run finished, the AMS will enter the run checker state to validate its output. So if the validation passed, it will enter the optimized resource state to perform some high-level auto-tuning if needed based on the actual runtime resource consumption until the runtime and the resource usage of the new version run beats the old version. And if the resource optimization is passed, then it will enter the ready-to-migrate state, and the job will be migrated either automatically by the AMS or manually by the operators based on the job tiers. And we can always easily roll back the job if anything wrong happened. And during the run checker state, If the validation failed, then we will rerun the job in the original version in case of some undesired input data change that happened externally. And during the process, if anything wrong happened, then we will enter the failed state where investigation is needed to resume the migration. There are some key components to make AMS resilient and intelligent. So in the prepare config state, it will first try to automatically infer the missing configurations from the historical executions. And it will only require manual input if the auto inference failed. This can help save lots of manual effort. And besides, the AMS is designed to automatically recover from some common failures, like the driver or executor out of memory. And we use checksum to perform the data validation by aggregating the hash value of the output data. There are some tricky cases which may bring some unexpected checksum mismatch. For example, some data fields might suffer from tiny float difference, and we need to convert the float field to decimal with fixed precision to eliminate the noise. And also, for complicated output field like the nested list, we need to sort the list first to remove the order bias. So once the job is ready to migrate, the AMS will send out email notifications to the owners. And for low priority jobs, owners are given 1 day to either reject or finish the migration. And if no actions are taken, then AMS will automatically move the job to the migrated status. For the high priority jobs, we require owners' manual confirmation to move the job to the migrated status on the AMS UI. And this is one example of the AMS job detail page. So besides visibility purpose, we also provide different buttons for easy management. For example, we can easily upgrade the Spark configurations by click the updating buttons here in the UI, or we can easily roll back the job to original version by click the rollback button. And we can always also manually ingest a new job by click the manual migration button on the top right. And after going through the generic challenges and solutions, we can then go one step further to look at the peculiar challenges for each Spark type, starting from the Scala Spark. So there are generally 3 layers for the native Spark. And the first challenge is the Scala compilation incompatibility. So basically, Spark 3 requires Scala 2.12 or higher, but the Spark 2 lives in Scala 2.11. And we need to upgrade all necessary Scala dependencies to 2.12. And for large modules, the complex and transitive dependencies can make the upgrade really tricky. In addition, in Pinterest, our central Scala repository is Bazelized following Bazel's one version policy. And currently, the global Scala version is 2.11, and it's infeasible to directly bump up the global version. So we need to figure out a way to support multiple Scala versions in Bazel. What's more, there are some semantic or syntax gaps during the migration, and we will give more details in later slides. So we worked with Pinterest CIP team to first add customized multiple Scala version support in Bazel, which paved the way for the Scala dependency upgrading. First, we will register multiple Scala toolchains in the global workspace, and then we utilize Bazel's platform concept to resolve different toolchains. Then different Bazel target will specify different platform via Bazel's tagging system. And at last, different CI pipelines will collect and filter Bazel target by different platforms so that they can be compiled and released under the correct Scala version. And big shout out to Pinterest CIB team, and thanks Jasmine and Eden. So these are some code examples on how we support this multi-Scala version model in Bazel. First, we implemented some customized function to support Scala multiple toolchain coexist without overwrite. Then we register multiple Scala toolchain and define different platforms to bundle with different Scala toolchains. And once the toolchains and platforms are ready, then for any Bazel target, like the unit test or any release target, we can specify the platform in the tag definition, like the graph here. So the corresponding Scala version will be used. We also added the platform option to the Bazel RC file so that we can specify different platforms during the local development. And once we have the multi-Scala version support, we can then upgrade the Scala dependencies. For external Scala dependencies, we will first try to identify the equivalent Scala 2.12 ones from the open source Artifactory. If it's not available, then we will choose the closest available version to minimize the potential syntax gap, and then upload it to our internal Artifactory. For the internal forked dependencies, we need to work with the owner team and rebuild them on Scala 2.12 and release to the internal artifactory. There are some empirical lessons we learned for the Scala version upgrading. So if you also use Bazel, please try to retain the same dependency order if possible, because the order change in Bazel can cause different dependencies to take priority. This can make a big difference if there are some transitive dependency version conflict or shading, and it may bring some errors like the class not found. In addition, when upgrading Scala dependencies to 2.12, we recommend staying at the same package version if possible. Using higher version may introduce some syntax gaps and bring incompatibility in the Spark 3. And what's more, for some large Spark modules, the transitive dependencies can be incredibly huge, but not all transitive dependencies matter for the migration. It will simplify the migration a lot if we know exactly what are used and only upgrade the transitive dependency on demand. And the last thing to mention is it's worthwhile to identify the necessary internal dependencies and communicate with the owner team to beforehand to align with the cross-team OKRs and avoid delay. So the last piece about the Scala Spark is the semantic and the syntax discrepancies, especially for the old Spark 2 versions. We've seen cases where the same code behaves differently across Spark versions, and here are some examples. The first case is the global Spark session and the Spark context, which is allowed in Spark 2.1, but it will trigger errors like the illegal state exception in Spark 3. And we need to move the global Spark session definition into the entrance function. Another case is like the auto-inferred partition column type when we specify the base path from the read option. Different Spark versions can auto-infer different column types. For example, the DT partition column here will be inferred as string type, but in Spark 3 it will become the date type. And one solution is to explicitly cast the this partition to expected type in order to retain the consistent behavior. And there are also syntax gaps when migrating to Spark 3. The first common case we've seen is the Spark jobs dependency conflict with the Spark 3 native dependencies. For example, some Spark 2.1 jobs relies on the Breeze 0.12. However, in Spark 3, the native dependencies is Breeze 1.2 with some incompatible syntax change. In order to solve this, we need to use jar shading to resolve the version gap here. The other case can be less frequent. Some open source pull requests are backported and bundled as part of the job code. However, those patches have gone through syntax change in later Spark version, which make the code incompatible in Spark 3 and cannot be resolved with shading. So we need to either maintain two versions of the code for the same job or backport the change into, to our internal Spark repo and decouple it from the job code. And compared with native Spark, PySpark is relatively easier to migrate, but there are some unique concerns we need to address. In Pinterest, the runtime Python environment can be divided into two parts. The one is the pip installed third-party libraries. The other is the internal Python codes. And previously, we only provide limited internal Python codes together with the third-party libraries. However, the internal Python codes can exist in multiple repositories, which make it vulnerable and hard to manage. And this can cause the migration fail from time to time unexpectedly. And also, for some PySpark jobs, they rely on the external Spark 2.11 jars, which make them suffer from the same Scala version gap as the native Spark. What's more, the row field names are no longer sorted alphabetically in Spark 3, which may cause the column order change. And the environment variable to support the sorting method in the official migration guide is also removed in Spark 3.1. So this is like the composition of our runtime Python environment for PySpark. And we take different actions to address these issues for PySpark migration. First, for the runtime Python environment, we refactor the structure, and Conda is purely used to manage the third-party libraries, which will be archived and shipped with the archive flag. In the meanwhile, we also provide complete internal Python code archives together with Conda archive during runtime. For ad hoc runs, the user's local code will be packed into archive files. And for production runs, we'll use the latest production code archive released by Jenkins pipelines. In this case, the runtime Python environment is clearly structured with complete coverage and reliability. Then for the external Scala 2.11 jars, we will take the similar approach to upgrade the Scala version. At last, for the sorting behavior change, We will check the column order in the auto migration service and apply explicit column order sorting if needed to ensure the consistency across multiple Spark versions. Now I hand over to Zahim.
Thanks, Siri. Next, I'll be going over the major challenges we ran into the Spark SQL migration. So the first thing we wanted to do for the Spark SQL migration was stop the inflow of Spark 2 jobs. This is important because we didn't want a never-ending stream of Spark 2.4 jobs to migrate. We accomplished this by first making sure all our ad hoc queries run on Spark 3 by default, while still allowing users to run Spark 2.4 jobs via a set statement. The next thing we did was for all our scheduled jobs, we built an allow list. Jobs that were allowed to run on Spark 2.4 were put in the allow list, and during execution of the job, a check was made in the allow list to see if we were allowed to run on Spark 2.4. If we were, we ran the job on Spark 2.4. Otherwise, we would run the job on Spark 3. As part of the Spark 3 migration, we needed to update Livy to support both Spark 2.4 and Spark 3. Livy, if you don't know, is a service that allows you to interactively run Spark code. Pinterest has a bunch of custom logic built into Livy that does fast syntax checking and fast DDL sessions. Fast syntax checking is essentially checking the semantics of the query before submitting it to Yarn. This allows users to get instant feedback on semantic errors instead of waiting for a Yarn container to be allocated. The fast DDL session is a similar improvement where we run DDL queries on Livy instead of running them on Yarn. There's no need to run on Yarn if all we're doing is dropping a table. In order to use Spark 3 APIs, we need to upgrade Livy to support Scala 2.12. This was a relatively easy change that required a few minor edits to the Livy codebase. Most of these changes were removing deprecated APIs that were no longer working on Spark 3. Additionally, we needed to launch the appropriate REPL driver based on the Spark version that the user had set. We would extract the version information from the query and make sure that Livy launched the appropriate REPL driver based on the Spark version that was used. The next thing we needed to do was to make sure that queries we tested on Spark 3 were safe and not affecting production data. We implemented a tool that would parse the Spark SQL query and rewrite it in such a way as to not affect any production data. In this example, you can see we make a copy of the output table and change the query to output to this new table. Next, we made a change to Spark to allow dashes and set statements. As part of Spark 3.2.2.5.7, dashes and set keys are considered special characters. In order to have a dash in the key, it would need to be wrapped in quotes. Unfortunately, many of our Spark SQL queries running on Spark 2.4 contain set statements with dashes in the keys. And updating these queries to wrap them with quotes would have been very costly for us to do. So instead, what we did is we made a small patch to Spark to allow dashes in the set statement keys. One of the biggest hurdles we encountered during the Spark 2.4 to 3 migration is that the default Hive execution engine was bumped up from 1.2.1 to 2.3.7. Unfortunately, Pinterest's Hive Metastore still runs on 1.2.1, and using the Hive 2.3.7 client libraries to communicate with our Metastore resulted in errors due to unimplemented APIs on the Metastore side. Our workaround was to set the spark.sql.hive.metastore.jars to use the 1.2.1 client libraries. Using this config, Spark would load the Hive Metastore client libraries in an isolated class loader and use the client instantiated in the isolated class loader to communicate with the Metastore. This does, however, cause some issues where the code within the isolated class loader starts casting to classes loaded by a different class loader. And you can get class cast exception errors. The solution was to add the class to the shared prefixes config, which will load the class using the base class loader. The other thing that happened was that our surveys no longer worked with Spark 3 due to the deprecation of the survey interface in Hive 2.3.7. This was a relatively easy fix of updating all our custom surveys to use the abstract survey interface instead of the deprecated survey interface. The last challenge we faced as part of the Spark 3 migration was to upgrade it was to use the native Parquet reader instead of the Hive Parquet reader. The Hive Parquet reader was originally used at Pinterest to make the migration from Hive to Spark SQL more seamless. The native Parquet reader is, however, much faster than Hive, and we wanted to see some of these performance improvements. However, this also led to some unforeseen consequences. The native Parquet reader collects stats on the size of the data while reading the Parquet files. The stats don't take into account the uncompressed data, and this led to a lot of broadcasts on sparse data sets that compress really well. When these data sets are uncompressed and loaded into memory, they become a much larger and can overload the memory available on the driver and executors. As a result, we had to significantly reduce the Spark.SQL auto broadcast join threshold to a much smaller number in the scenarios where this happened. The other issue we ran into when using the native Parquet reader was that it had no mixed partition support. So if you had partitions that were written in a format other than Parquet, it would fail. This was particularly problematic for us as we were doing a migration to Parquet during the same time. Tables that we converted to Parquet had old partitions that were in other formats, while newer ones were in Parquet. For these data sets, we had to turn off the native Parquet reader, but we are planning to update the native Parquet reader to support reading from mixed partitions as well. So far, we have migrated 60% of our existing workload to Spark 3, and we have seen upwards of 45% improvement across the vCore and memory usage, and over 60% improvement in the runtime of jobs. Our plans for the future include continuing to migrate the remaining Spark jobs, support for Scala 2.12 on all our existing jobs and libraries, Spark 3 kernel support on Jupyter, and Bazel dependency multi-version flexibility improvements. And also, we are working on generalizing the migration service to support all types of migrations. Yeah, here are some upcoming talks by Pinterest. We have an improving interactive query experience on Spark SQL led by our colleague Ashish from 4 to 4:35, and then a deep dive into the Hive to Spark SQL migration led by me at 4:45. Thanks for joining our session, and we'll be here for any questions.